think about RNA-seq data. So you have a pool of RNA, and there's many different kinds of transcripts. And when we're going to go put it on a sequencer, we take a sample. So you can imagine that there's a number of transcripts for a given gene that could be quite small proportional to the total amount of molecules. So that makes the probability of one of those coming out quite small. But now we take a big sample and we're summing all these transcripts that come out. So you can kind of see where the Poisson distribution would apply here. You're now counting the number of samples, the number of transcripts that come out. And again, if the probability of a specific gene coming up is small, but because we take such a big sample, we might get 1 to 10 counts. That's a case where we would think that the Poisson applies. So if in fact the Poisson applies, then we have that every gene follows a Poisson distribution with the rate of that distribution, the average of that distribution has to do with how much of that transcript is available in the sample. So how can this be useful in practice? So one of the ways we can use this model, we're modeling now with the Poisson, is we can predict certain characteristics of things like the ratio of counts. So in biology, people are many times interested in the log ratio, comparing two samples. So one of the things that we learn from the Poisson approximation is that low expressed genes, if you take the log ratio, are going to have much bigger variances. So what I'm showing you in this plot is a simulation where I basically I simulated data from two samples, some genes being more expressed than others. I took Poisson distributed variables and then I formed ratios. If the denominator or the numerator was 0, I took them out. I only show you the positive values. And what we see, here's the log ratio, and here is the expected number of counts for each gene. And you can see that for less expressed genes, variability is much bigger. So that is already a cautionary tale using just modeling and statistical theory, what we should be careful about when we actually analyze RNA-seq data. Here's real data. Now what I did is I took the counts for all genes, and what do you see? Pretty similar behavior. Small expression, bigger variance. So this is a case of how modeling can be useful, as George Box told us several decades ago. All right, now, when we look at this a little bit closer, there's an important distinction we have to make. That variability that we described earlier that helped us motivate the Poisson approximation, the variability was related to the sampling variability. And in that previous plot that I showed you, I was showing you technical replicates, where all the variability comes from sampling. Now, if you look at biological replicates, the story changes, because now, as we showed in an earlier module, there's biological variability. Now, is that Poisson? There's really no motivation for that being Poisson. And in fact, if you assume instead that the biological variability follows a gamma distribution, we're going to learn about gamma later in this module, then the distribution across samples is no longer Poisson, but instead it's negative binomial. So here's a plot that is confirming that when you have biological replicates, the data does not follow a Poisson distribution. So how am I doing this? You can show mathematically that the variance of a Poisson is equal to its mean. So when I have real data, I have 4 biological replicates here. I can compute the sample mean and the sample variance plotted against each other. And they should fall on the identity line. But as you can see in this picture, the variance is larger than what is predicted by the Poisson. In later modules, we're going to learn that the negative binomial fits the data much better.